Hello and welcome to this video on catalysis. This will be suitable for Year 12, OCR A, and maybe if you're a very interested GCSE student, as all of mine will be. What we've got here is an energy profile. This is a simple exothermic reaction, and we've got energy and reaction coordinate, and here obviously we've got our reactants R and our products P. Now, there are normally two labels that you would typically add to this diagram. The first is delta H, okay? The energy enthalpy change between the reactants and the products. And that is not influenced by a catalyst. The second label is the activation energy, EA. So that's the level that's basically required from the reactants. How much energy do you need to put in order to have a successful reaction? Now, what a catalyst does is a catalyst provides an alternative pathway of lower activation energy. So we have a lower pathway, smaller difference between the reactant level and the top of the curve. And what this means is we get a faster rate of reaction because more particles have sufficient energy to become products. So if we look for a definition of catalysis, we can say a catalyst increases the rate of reaction without being consumed by providing, probably need some commas, by providing an alternative pathway of lower activation energy, EA. Okay, that's our definition of a catalyst, and the important thing is that it isn't consumed. That was smooth. It isn't consumed, okay, and it is free to use again and complete the same process. Now, there are two different types of catalysis, and I'm going to look at the first one now. So, one type of catalysis is homogeneous. This means that it's in the same physical state as the reactants. So, a good example of this would be if I take ethanol, okay, alcohol with 2 carbon atoms, and react it. I'm going to draw this the other way around so we can see what's eliminated. If I react it with ethanoic acid, now we should know esterification reaction is what's going to happen here, and the catalyst for that is H2SO4, sulfuric acid. Okay, so what we're going to do is we're going to eliminate OH and H. Okay, the H from the alcohol, the OH from the carboxylic acid, and they're going to be eliminated as a small molecule, so we could call it an elimination reaction, condensation reaction because it's water, and we are going to produce our ester. So the ester in question is this. which is ethyl from the alcohol, ethanoate from the carboxylic acid. We've got another product here. As I mentioned, we're eliminating water. So that's an example of homogeneous catalysis. We've got two reactants that are liquids, and we've got, although they of course may be aqueous solutions, but I'm talking in terms of a state, and we've got a catalyst that's going to form some sort of intermediates, and is obviously in the liquid phase. Now, this reaction, obviously, as well as being an example of homogeneous catalysis, is an esterification reaction. So, the other type of catalysis is heterogeneous catalysis. Now this is in where the catalyst is in a different physical state. Okay, so we're looking at something like a solid. So if we take ethene, which is in the gas phase, and react it with hydrogen, hydrogenation, we need a nickel catalyst, and we are going to produce ethane. Excuse the condensed reactions, I've got a whiteboard width issue. And we produce ethane. Now, this obviously heterogeneous, but I'm going to take a little look at the mechanism so that we can understand the two processes that take place. Got a much more shortage-friendly version of my loo roll in this video. We're going for a J-cloth. So, if I imagine the surface, which is nickel, I will have an adsorption to the surface of my reactants. And we can see here how the hydrogen has joined onto the surface, as has the alkene. So that's an absorption step. The reaction will then take place on the surface. The atoms will be rearranged. This hydrogen will join on with that carbon, and then that carbon will finally join on with that hydrogen. And then we have the kind of second part, which is, well, third part after the reaction, the desorption process. And that's where my product leaves the surface in a desorption step, and my catalyst is regenerated. The surface is back to normal, just as in the homogeneous catalysis we looked at, the esterification reaction, the sulfuric acid catalyst would be regenerated. So there's your two types of catalysis. Obviously, other examples that are common with the heterogeneous catalysis, we've got iron in the Haber process for making ammonia. And in the homogeneous, we could look at radicals as a common source of catalysis, where they're regenerated in the depletion of ozone, looking at chlorine radicals. The final thing to mention is that whilst these catalysts are regenerated, in real terms, when companies are using them to increase their rate of reaction without heating up or adding more pressure to what they're doing. So catalysts are really useful in that way. But what is important to mention is that these catalysts do have a turnover number, an amount of moles, if you like, of reactant that they can catalyse before they do die. So catalysts are poisoned in the end, and are no longer able to do this adsorption, desorption, or to form the intermediates if they're a homogeneous catalyst. That's just some extension that you may want to read about after this video. So thanks very much.